Welcome back. This is an Aleks training video on calculating the acid constant of a weak acid from pH. Pretty hard problem, I think, but I will try to do it slowly and explain as best I can. The case of A is the constant that tells you whether you're going to have more products or more reactants. And I've given you the expression here. Case of A is the concentration of hydronium, and all this comes from the balanced equation. So I gave you an equation, and let's see if you can derive the equation yourself. Here's butanoic acid, okay, big ugly whatever it is, acid. It's not one of the 7, so it's a weak acid. That means it's going to not completely break apart into hydrogens and the CH4, or the 4-carbon group, whatever the conjugate base is called. And then it's going to react, that hydrogen is going to come off and react with the water and form hydronium. And then whatever your leftover, whatever your conjugate base is left over. So it's the same as all the acids we've done. You take one of the acids off, one of the hydrogens off the front, add it to the water, it becomes hydronium, and then whatever's left over becomes your conjugate base. Okay, so that is the balanced equation. Now, it's already balanced. It's a 1-to-1-to-1-to-1 relationship. And that's important because remember, when you're doing the expression, we're doing the acid expression, the constant expression, these coefficients become superscripts, or it becomes powers, exponents, on these concentrations. So if this were a 2, then this would be this concentration squared. Okay, but this happens to be all 1s to 1s to 1s. Okay, so it's saying that the pH is 2.82. And the pH, remember, is 10 to the negative 2.82 is the concentration of hydronium. Now, I told you before that when you're doing complicated problems, the easiest way to do it is to use an ice. This is called an ice table. Initial is your original molarities. The change is what's coming up or down. And then the equilibrium is what you have at the end. And it's these numbers in the equilibrium that you're going to put in these concentrations to find your case of A. So let's take it slow and do it. So first of all, let's do the easy stuff. We're going to do the doing the ice table that we know. Okay, so the first thing that we said is that it is a 0.15 molar butanoic acid. Okay, all right, so if it's 1.5 molar butanoic acid, then that is what we're going to be put here. This is 0.15 molar. That's the initial molarity. Now, if you come back to the balanced equation, you'll see that that's on the left. Okay, you put it in water and then it breaks apart and then adjusts with the water and then starts making acid. Right? So originally on the right, there isn't any acid. Okay, so that's a 0. And there isn't any conjugate base because it hasn't started yet. So that's the initial. Now, what is the change? The change is that you're going to get some acid production. So we'll just call this X. Then we'll find out what X is in a minute. So if X is on the right, and this is a 1-to-1 relationship, okay, so there's no coefficient, there's no subscripts here, or coefficients here, then for every X here, that whatever number of moles here that I have the same number of moles here. So that means this is also going to be X. And if this on the right is X, and this is a 1-to-1 relationship over here as well, so it's going to be 1X, but it's negative. It's on the other side of the arrow. So this is going to be minus X. Right? So this then will be total. All you're going to do is add this together. You're going to get 0.15 minus X. You'll have X, and you'll have X. So let's find out what X is. X is the pH. So it's the concentration of the hydronium. We need to know what the new concentration of the hydronium is. So when the butanoic acid breaks apart, that hydrogen is going to join with the water and make some acid, make some hydroniums. And then that hydronium concentration is going to get bigger, bigger, bigger until it's in equilibrium. And it's the case of A is finding out what is the equilibrium. So the change is going to be that change in acidity, or this change in the concentration of the hydronium, the H3O plus. So how do I find it? Right, you're going to find it by finding the concentration of the H3O plus. The concentration of the H3O plus is equal to 10 to the minus pH. Well, that is equal to 10 to the minus 2.82, and 10 to the minus 2.82 is 0.0015135561. Okay, so let's go to 4 places, 1514. Okay, that is your X. So this is going to be 0.001514, 0.001514, negative 0.001514. All right, so this is going to be 0.15 minus that. So it's going to be 0.15 minus 0.001514. Well, what is that? That's going to be, I'll just do it to 4 places. Put it a little bigger, to 0.1485. Okay, and then this is X again, 0.001514 and 0.001514. Once you have these numbers of equilibrium, you can take these numbers of equilibrium and put them in as the concentration and simply solve for case of A. So I have got case of A is equal to, I need the concentration of hydronium. So the concentration of hydronium is here, okay, because remember it's the equilibrium number. So this is going to be 0.001514 times, second one is the concentration of the C4H7, that's here, it's the same number, so it's going to be 0.001514, and then I'm going to divide that by the equilibrium of the butanoic acid. The butanoic acid is the stuff that's on the bottom, HC4, which is going to be 0.1485. So when I divide that, I multiply the top two, divide for the bottom. I'll do that for you. 0.001514 times 0.001514 divided by 0.1485. I get case of A equals 1.5. Let me just go ahead and find out how many significant digits that I need. I'm going to, let's see, 2.82 is 3 significant digits, and 0.15 molar is 2, so it has to be 2. So it's going to be 1.5 times 10 to the minus 5. That means the very much more product. So it's a weak acid, so it's not going to dissociate very much. It's just going to be very, 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 it's not going to break up very much. You're going to have mostly butanoic acid in the water with a little bit of hydrogen, a little bit of the conjugate base. Now, I would love for you to see what I can see here. That means that I can take a pH tester, which costs $15, put it in a solution, find out the pH, and from that little piece of data, knowing that I put in a certain concentration into some water, I measured the pH and got it as a certain number, and from that data, I know how much of that acid broke apart and how much didn't break apart. So, hard problem. I think this is hard, but useful, useful, useful. All right, we'll practice. We'll practice this.